All right, today we're diving into a story that sits right on the mind-bending edge of mathematics and physics. It's about a geometric object so powerful, so precise, that it's been called a perfect mirror of arithmetic itself.
And I want you to start with this question. Just let it sink in for a second, because it's really at the heart of everything we're about to explore. What if there was some kind of shape, a manifold, that could peer deep into the very structure of numbers and just tell us their secrets?
And this leads us straight into the central paradox of this whole story. This object can read with almost unbelievable clarity, but it seems completely unable to write. It can't change or constrain what it sees. Now, this isn't a bug, it's a feature. And understanding why? Well, that's the journey we're on today.
So, first things first, what exactly is this object? And how in the world does it act like a perfect mirror for the world of numbers?
Okay, so the object we're talking about is this really unique kind of three-dimensional sphere. The easiest way to think about it is to picture the surface of a ball, but, in higher dimension. Now here is its superpower. Its own geometric properties, you can think of them like its vibrations, perfectly, and I mean perfectly, reflect the hidden patterns of prime numbers. And these patterns, they're encoded in these mathematical tools called L functions, which are kind of like the DNA for the whole world of arithmetic.
And here you can see that reading power in action. When we measure different geometric properties of this sphere, like its twist or its energy levels, we don't get some messy, complicated jumble of an answer. Nope. Instead, the results just cleanly break down into these fundamental building blocks of number theory. It's kind of like popping the hood on a super complex engine and finding out it's made of just a few perfect, simple parts. It's beautiful.
And just how well does it read? Get this. The connection between the geometry and the numbers has been verified to 79 digits of accuracy. 79! That is not an approximation. That's a deep structural truth. This mirror isn't just good, it's flawless. But here's where things get tricky. The mirror has two different ways of reading, and this creates a crucial tension. Imagine you have two tools. One is like a laser pointer. It can highlight one tiny detail with incredible precision, but only in that one spot. The other tool is like a floodlight. It illuminates the entire landscape all at once, but you can't really pick out any single detail. The big dream, of course, was to somehow combine the laser's precision with the scope of the floodlight. And this brings us to the next big chapter in the story. With such a powerful reading device, could we use it to actually do something? Could we turn this perfect reader into a writer?
I mean, think about it. If this object can see the landscape of prime numbers this clearly, then maybe, just maybe, it could be used to pin down the location of L function zeros. And let me tell you, that is a huge deal. We're talking about something directly related to the famous Riemann hypothesis, which is one of the biggest unsolved problems in all of mathematics. The stakes really couldn't be any higher.
And so the attempts began. And look, this wasn't just one or two tries. This was a systematic, full-on assault. Researchers attacked the problem from every single angle you can imagine. They tried to manipulate the shape's geometry, to isolate the mathematical functions, to find entirely new ways of measuring it. They even tried to change the fundamental language of the encoding. They literally tried everything.
And the result of all those attempts? A complete and total wall. Every single strategy failed. And it wasn't even that they almost worked, or that the calculations were just too hard. Nope, each path led to a definitive structural dead end. The mirror would show you everything, but it absolutely refused to be used as a tool. And the reason for this failure wasn't just a single locked door. It was a fortress. There were fundamental issues with the math itself, problems with how information was encoded, a total disconnect between the languages of geometry and arithmetic, and ultimately, a realization that the mirror wasn't even hiding anything. All the information was already right there, out in the open.
So why? Why does this perfect reader refuse to be a writer? Well, the answer is the climax of our story, and it's a beautiful and profound concept called the curvature duality. It turns out, a single property of this space, its positive curvature, is doing two completely different jobs at the exact same time. From the perspective of physics, this curvature creates what's called a mass gap. That's essentially the reason why the smallest particles can't have zero mass. It's fundamental to our physical world. But from the perspective of arithmetic, that very same property builds the wall that shields the secrets of the prime numbers.
So here's how it works. In physics, positive curvature leads to the mass gap, which allows matter to exist as we know it. In arithmetic, that same curvature creates this tiny mathematical shift, but that tiny shift is enough to activate an infinite mathematical structure, a kind of shield, which is the very mechanism that blocks our access. The crucial point here is absolutely mind-blowing. The property that allows particles to have mass is the exact same property that makes the secrets of primes inaccessible.
And there it is, the brilliant resolution to our paradox. The object can't be used to constrain the primes because the very geometry that allows it to read them so well is the same geometry that has to protect them in order to create mass. You can't have one without the other. Creating mass and getting spectral access to the zeros are just fundamentally in opposition.
So if the object can't be used to solve the Riemann hypothesis, was this whole journey a failure? Absolutely not. It just means we were asking the mirror the wrong question.
I mean, just look at what this mirror is showing us. It's not just abstract data. It's reflecting the fundamental constants of our mathematical universe, the first primes, the golden ratio, the Riemann zeta function itself. It's not just reflecting numbers. It seems to be reflecting the very blueprint of mathematical reality.
And this is the final beautiful twist. What was a dead end for number theory turns out to be a stunning predictive tool for physics. The same geometric structures that passively read the L functions can be used to actively predict physical realities, like formulas for the masses of fundamental particles and even why particles seem to come in 3 distinct generations. The mirror wasn't a tool for solving math problems. It appears to be a blueprint for reality itself.
And that's where we'll leave it. The inability to write wasn't a flaw. It was the entire point. The geometry of this space provides a perfect, passive reflection of the deepest truths of arithmetic. And in doing so, it just might be showing us the mathematical bedrock upon which our physical reality is built. And that leaves us with a final question. What other truths are waiting for us, perfectly reflected in the mirrors of mathematics?